Question 3 is about double slit interference, and the first part asks us why a laser is used. Well, a laser is used because it's a coherent light source, where coherent means that there is a constant phase change between the two sources, i.e. the two separate slits that are available. Part 2 then asks us to do a calculation where we are asked to determine the separation of the points of maximum intensity upon the screen. So in the formula booklet we get given that little s is equal to lambda over d. Let's identify what these are on the information that's given. So the wavelength is stated here as being 700 nanometers, so that's lambda. The separation from the screen is given here, and that's d, the distance from the double slit to the screen. Little d is the distance between the two slits, so that's given here. It's important to note that all of those need to be in the same units, so meters, in order for this equation to work correctly. So we can then use S equals lambda d over d, plug in the numbers that we've got, so we've got 700 nanometers times by d, which was the separation, 2 meters. And then little d was the spacing between the two slits, which was 0.5 millimeters, or 5 times 10 to the minus 4 meters. If you plug that into your calculator, it comes out as 2.8 times 10 to the minus 3 meters, or 2.8 millimeters. Part 3 asks us to describe the effect that increasing the number of slits would have on the intensity pattern on the screen. When we increase the number of slits, there are two main effects. One is that it sharpens the maximum, and what I mean by that is that they become narrower. It also ensures that there's a greater contrast between the maximum and the minimum, and that just essentially means that there are brighter maxima compared to the areas of destructive interference. Part B then replaces the double slit with a diffraction grating and asks us to work out the the number of positions of maximum intensity that will be observed on the screen. So we know that for a diffraction grating, the pattern spreads over a much larger angle. In fact, it gets as far as 90 degrees. 90 degrees would be the furthest that you'd expect to see a maximum. That's what we're going to use that effect in the equation. D sine theta is equal to n lambda, the equation for diffraction grating. Let's identify what we've been given in the question. We're told that there are 3.5 times 10 to the 5 lines per meter, which will allow us to calculate d. D is the spacing between any two slits. So in order to calculate that, we just do, if there's 3.5 times 10 to the 5 every meter, we just do 1 over 3.5 times 10 to the 5 in order to get d. N here is what we're trying to find, and lambda was given in the question. So we can rearrange that to get n equals d sine theta over lambda. The d we've said is 1 over 3.5 times 10 to the 5. Sine theta, look, remember we're looking to try to find the maximum number of lines that are possible on the screen. So we're going to put sine theta equal to 90. So if theta is equal to 90, sine theta becomes 1, so we can get rid of that. Or just put times 1 there to remember that we've done it. And then we need to put in the wavelength. That goes down on the bottom, and it was 700 nanometers. If you plug that into your calculator, you should come out with an answer of 4.08, which means that we then always round that down to say that the maximum number that we would get is 4. Don't forget though that this at the moment is we're only talking about in one direction. These are the number of orders which are either side of the central maximum. So that actually turns into a total number of positions of maximum intensity, 9. In case you're not sure why this is, this diagram might help. So here is our diffraction grating. If we imagine that light is coming through here, we're going to get a central maximum with n equal to 0, and we've just calculated that the maximum number of bright fringes that we will get to one side of that is 1, 2, 3, 4. That's with n being as close to 90 as we're going to get. But we've also got that in the other direction as well. So I've only drawn 2 on here, but we'd also have 4 on this side, giving a total of 9.